everyone. I'm Kylee here. I'm the CGI software lead, and for the next 20 minutes, we're going to do a really high-level speed run of the CGI software. It's very complicated, very large and complex, but we'll do our best to cover the basics of it. So we'll start from a systems perspective. So CGI pretty much can be divided into these 13 functional domains that are displayed in this visual here. We have the behaviors layer. Okay, so CGI is pretty much divided into these 13 subdomains. We have like the behaviors, the functions, and the infrastructure layers. So the behavior layers cover things like LOFIS, COFIS, alignment and calibration, etc. The functional layer is closer to the hardware, so we have things like XCAM, LOCAM, and the DMs. And then at the very bottom, we have the instrument control, electronic, and flight software infrastructure layer. So for each of these domains, to kind of translate CGI requirements into flight software requirements, we developed functional design documents that kind of describe how this CGI flight software should operate. So still at the systems level, there are kind of 4 terms that we should understand when we're talking about CGI flight software. The first of these is a channel, which is a telemetry data point. So it's a map to a single source, and these are things like temperatures, parameter values. We have monitors. So for fault protection on CGI, fault protection is continuously running in the flight software to detect potentially dangerous conditions on the instrument. If these are detected, if a monitor is triggered, then the instrument will go into safe hold to protect all of the hardware. So it will power things off and put the instrument into a safe state. So we can kind of intervene, see what happened, and continue. The next is a parameter. A parameter is a non-volatile value stored on board. We modify these via commands. So regardless of power cycling of the instrument, these values will remain in the onboard message. And then we have commands. That's kind of self-explanatory. It is an input to flight software that initiates some behavior. So examples of commands are things like powering the hardware, closing the Zernike loop, and taking pictures with the camera. Next, we have this big chart full of numbers. This is just to give you an idea of the complexity of CGI flight software. You can see for commands, parameters, channels, and monitors, we have hundreds, if not thousands, of these data points. That's a lot of information stored in CGI flight software and being transmitted back and forth to the ground and the instrument. So the lines of code in CGI flight software right now total 104,000. A typical instrument is 30 to 70,000 lines of code. So that alone gives you an idea of the level of magnitude more complex that this instrument is compared to normal instruments. Ground software, by comparison, has 107,000 lines of code, and the FPGAs have 60,000 lines of code. One note to make really quickly, we won't go into detail, but for CGI flight software, we did have to modify an open source linear algebra library. We utilized Eigen. That's not really considered in the lines of code or in this table, but you do have to remember when you're doing flight software in an instrument in orbit, you can't just pull the Python library and run Python. So we did additionally have to modify a linear algebra library to accomplish things like HOFIS, GLOFIS, with a wavefront sensing and control algorithm. So to simplify the CGI flight software, we did things like we used code reuse, so fault protection, telemetry, the parameter table. These were pulled from legacy instruments that had heritage code. That simplified. We didn't have to reinvent the wheel for every little piece of the flight software. We utilized command and telemetry dictionary management. So again, you see we have 2,000 plus channels coming out of flight software. Those have to be defined, given a format, given enums and arguments. So we had to have a really good software configuration set up to keep track of all of these data points coming out of CGI flight software. And then we utilized some auto coding specifically for the PAMs. You can see there's 443 channels coming out of the PAMs. If a human were to hand code that, they would lose their mind, but also probably make mistakes. And so we utilized some auto coding to simplify that process. And traditional software techniques like camera class inheritance. So XCAM and LOCAM do share code between them, and that also cut down on the code base size. Okay, so going into more of the software side of things. CGI software is written in C++. It uses the VxWorks real-time operating system. It runs on a Leon 4 processor on a GR740 board. It is a rad hard board, and it utilizes a single core software design It is a multi-core processor board, but we use one for simplicity. The code base was developed over 5+ years by a team of anywhere from 1 to 6 people. There was a core team of 3 people for the most part. It is NASA Class C software, meaning it's necessary for the science return from a single instrument. And that being said, we do comply with strict JPL flight software coding standards. And we do this because if the CGI flight software were to go down and never come back up again, CGI would be a really expensive piece of space junk because we can't communicate with it anymore. So we do in flight software have to meet really stringent coding design principles. We can't use dynamic memory allocation and we can't do recursive function calls, among others. And I just really want to drive home the point that CGI flight software and flight software in general is very different from modeling on a desktop computer using Python or Pandas or NumPy. You have to be very careful that it remains responsive because you can't go power cycle it like you can your desktop computer. Okay, so at the bottom here in this big block diagram, we have a high level idea of what's going on in CGI flight software in general. So you see that we have ground interfacing through Roman. Obviously, that's a lot more complicated than just a line, but the key component to flight software is that we're receiving commands and parameters and we are sending telemetry out. Inside flight software, we have the behavioral state machines and the functional state machines. These are running kind of alongside each other, behavioral, commanding, functional. Additionally, we have about 4 tasks running that do other CGI critical tasks. These are the WFSC task that does all of the math for all the wavefront sensing functionality. We have the focus and Zernike control loops and the pointing acquisition and control loop. So these are all running in addition to the state machines to accomplish CGI objectives. On top of that, we still have to do instrument flight software work, which is fault protection monitoring, telemetry, parameters, memory, and ACS disturbance handling. So I'll mention this briefly, it will come up again later. ACS disturbance handling, we have to do because it's been mentioned before, but CGI will occasionally lose its stability requirements. And so we kind of have to put the instrument into a safer, but not powered off state while that ACS disturbance passes. And so we do have to constantly monitor for ACS messages from Roman. When those occur, we go into what's called inactive mode, where we kind of put things in hibernation, but not power them off. And this will come up because it's a complicated programming task in CGI software. Oh, thought architecture. In any given 200 milliseconds, this is an example of what CGI is doing in 25-minute slots. We're either processing messages, checking the fault monitors, or controlling. And do note that and you'll notice that we do have margin built into the slot architecture. Okay, for time purposes, we'll kind of skim over the stuff on the left. If you're interested in DevOps, this is what actually developing CGI flight software involved: GitHub, continuous integration, static code analysis. The important part is this diagram on the right. So for every release of flight software, the team would define the scope of the build, develop it, release it to the test bed, which Tim is the next talk for the FTB. The test bed team would run their testing, find anomalies. We would address them as a team, decide if it required a flight software update. If it did, we would do a point release of flight software and continue in this cycle until we were satisfied, at which point we would go to software requirement certification review, or SRCR. And this is when the project would get together. We would show our test results, show our code, and we'd all agree that it looked good and we were good to release. So that's how flight software development went on a day-to-day basis. Here is the functional test bed. Pictures on the left and right. The right shows an example of testing flight software on the test bed. The FTB was really critical for flight software development and for B&B, because if we don't have a test bed to run our code on, we're kind of just writing hopes and dreams into a text editor, and we have no idea if it's actually going to work on anything. So the FTB was critical. We used written test procedures, verification activity plans, and PBATs. Because these were written down and like configuration controlled, they allowed us to do regression testing. So for every new flight software release, we were able to go back with FTB and the B&B team and make sure that we hadn't broken anything either that was previously working in flight software. And Tim will go over this in more detail probably, but we use the telemetry data system Grafana that the FTP team provided. And these provided a good graphical way to like analyze data, what had happened over time in the test bed, the state of all of the telemetry coming out of CGI. And this was effective in allowing us to investigate anomalies quickly. So Grafana is great if you want to use that in the future. And real quick, this chart is our JIRA anomaly report burn down. The trend is what you might expect. As we continue testing, we find more and more issues in the flight software, but we also close them as time goes on. And so as our testing developed and our code developed, we reached a point where I think we were all in agreement, and then the things converged down to 0. So we have delivered and we don't have open anomalies at this point. Okay, I do have some data. So the most important piece of data to talk about is the CPU utilization with CGI flight software. You'll see that we sit at about 20%, which is great because the institutional guideline is 70%. When we want this 30% margin on the CPU, because again, we have to run critical instrument flight software housekeeping tasks like the fault protection. And we have to make sure that we can continue talking to the ground. So we can't just run an algorithm on the CPU at 100% for 7 days because we'll become unresponsive. We might miss an attitude control system disturbance. We might miss that something is getting too hot on the instrument. So we do have to maintain that margin on our CPU usage. We do get up to 72% for less than 1 second utilization. This is for HOFA's Gittle, which makes sense because it's the most intensive thing that the CGI software does in terms of computation. But that would only occur less than 3% of the time at TVAC. So on the right here, I won't read you these numbers. We're well within margin for packet throughputs and memory usage. Okay, so the last 2 slides are issues encountered in the development of CGI flight software and the lessons learned. So one of the biggest things that would pop up, which I kind of mentioned earlier, were there were dictionary inconsistencies. So between the dictionary that defined parameters, defaults, min and maxes, and the flight software, if we had discrepancies, the telemetry system wasn't able to parse these correctly, so we were getting bad data back from the instrument. So in the future, we would probably auto code from a single point of truth so that we don't get these disagreements over and over again for literally thousands of data points. We did have resource contention issues. This is kind of inevitable when you have an instrument made up of multiple submodules that are all communicating with each other. 2 electronic slices shared a spacewire port. So if one of them was talking, the other couldn't, and we got into software situations where they might deadlock each other, where they're waiting for each other to talk, but someone is holding the line and not releasing it. So these are things that you have to consider when you're designing a system that's so complex with so many moving parts, is how they're going to interact, and you have to order your operations. A way that we addressed that for the WFSC task is we implemented high and low priorities. So we said this instrument or this operation is time critical. It has to finish first. Anything else can wait in the background until it's done. We are flight software, but we're still just software. So we had some software bugs that you might expect for any code, state machine flow errors. An important one to consider when you're doing algorithmic computation like CGI does is floating point issues. This especially comes up because we have HOFA's Gittle, where the ground is involved, Python processing or desktop processing is involved. It's generating results in perhaps a different floating point format than we use on board. And so this actually happened in testing where we generate a float that's valid in a desktop, but when it was sent to the instrument, it crashed because the processor was not configured, or for instance, subnormal floating points. So keep that in mind. The biggest issue I think we had that we could remedy in the future is we had incorrect or missing asynchronous behavior. Asynchronous programming is a big, complicated thing, but for this context, what it really means is that we have all of these things running at the same time. So these tasks are running when we're running state machines. And if they, so for instance, the ACS disturbance loop, if it detects an ACS disturbance, it will tell the state machines to halt. But the state machines can be running an operation already, and you're going to halt it randomly, kind of, in the middle of this execution. You've now created exponential code paths where it can be stopped and reset at any time in its execution. We didn't design this from the beginning with this in mind. And so the base classes didn't have an abort mechanism for us to go into an active mode and come back out of it autonomously, which is what CGI does. And so we had to go back and kind of paint that onto existing code. In the future, if you're aware of this from the beginning, you can design your code a little differently from the start to accommodate this asynchronous behavior. A related topic is semaphores for resource locking. So if everyone is using memory or if everyone is using a WFSC task, again, if you're randomly told to go into an active mode, you have to make sure that you release all of your locks or else we again end up in a deadlock. And then the hardware itself also was not always robust to asynchronous commanding. So if we told the camera to halt taking pictures, and then we came out of an ACS disturbance and tried to resume, it would get into a funky state where it wouldn't necessarily accept new commands. So we did have to power cycle that. So that's an example of a lesson learned, where the earlier you define your asynchronous behavior needs, for example, the better you can incorporate it into both hardware and software, because both need to be designed a little differently if you're going to do things like that. Obviously, you want all requirements as early as possible, but that's the one that came up over and over again. And is really critical for this type of technology. We had a good build and test process on CGI. Tim will go into it more, but we had a good test bed, a good release process, and we were able to trace requirements to B and B effectively. One note is that COTS hardware can cost more. So there are an increased number of electrical interfaces between the processor and the hardware. And if something comes up where any piece of that pipeline doesn't behave the way that you need it to, you're going to have to work around that. And usually that ends up being a software solution. And so you might have saved cost and schedule on the hardware, but it has been moved to software in some instances. So just keep that in mind. We were really careful about software documentation. So we had good commenting diagrams, notes on this whole complex piece of software, danger zones. You do have to keep in mind knowledge turnover, workforce turnover. People are gone, they need to record what they know, so it can be maintained for years to come. And lastly, a big question that Eric Katie kind of touched on yesterday was HOFIS, GITL, or onboard. Obviously, CGI uses HOFIS GITL, and that is because there's a computational gap between requirements and what CGI Flight software and hardware can actually do. We only use one core. The original all onboard HOFIS design used a second processor board. He did not have the cost or schedule to develop an entire second processor board. And it's also important to note that it's not linear. You can't just copy and paste it and make another board. You now have to have software and electronics that communicate between the two boards. So it was probably a really smart decision to move part of the software requirements to the ground and do HOFIS GITL. Because you also can't forget that you need margin on the CPU. You can't just have it running an algorithm for days and days and days, because the instrument would inevitably just crash. And then you don't have anything. Why do you run it? You can't communicate with it anymore. So pretty much you can start by just having all of your software requirements defined and then partitioning them between the flight and the ground. Decide what needs to be in flight and what you can get away with putting on a ground in the loop system. That's my talk. If you're interested in more about the math library modifications, I did publish a talk on this a couple of years ago. And yeah, thanks.
Have any quick questions? Kylee? Yes.
So all these control parameters, you want to update them? Is it just a memory patch, or is it hard to do that, or is it easy?
Oh no, for the parameters, it's very easy, and that's why they're parameters. So they're just stored in MRAM, so they're persistent. So in the code, all that we do is we get your parameter name, we get what you want to set it to, and then we write to that location in memory. And then when we want to use it, if an algorithm uses it, it just reads from that location in memory.
Is that like in the scripts that or the commands that you send up, you put your code in parameter?
Mm-hmm. So there's like set parameter float, set parameter int, things like that.
Okay, thanks.